So one of the most common applications of the radiation effect is, does the thermometer actually read the temperature of the fluid in a channel, or is it the temperature of a fluid plus an additional correction term which we can reduce? So in this video we'll tell you the effect of the radiation heat transfer between the thermometer, sensor and the wall, and the convection transfer that happens through it. So the first thing, when you measure the temperature of a fluid in a channel flow, you put the thermometer in the fluid, and the thermometer reading is, you can get the thermometer reading through the thermometer sensor. This sensor actually reads it because of the heat transfer that happens from the fluid to the sensor. Now we know that the heat transfer from a fluid that's in motion and to a surface is by convection. So when you put a thermometer into a fluid, you will see that the temperature is at a certain value and it starts to slightly increase after some time. So after some time, you will notice that the temperature is constant. That temperature is known as the temperature occurs when equilibrium has reached. So when that equilibrium temperature is reached, the thermometer will give a constant reading, and that is supposed to be the fluid temperature. But however, in certain cases, when the temperature of the wall can, however, there can also be heat transfer from the temperature of this wall of the channel and the sensor. So in this video, we will look into the net radiation effect of these two things on the sensor, and how can we counteract this, and so that to give a maximum, so that to give a close approximate of the fluid temperature. So the first thing, the thermometer will give you a reading after equilibrium is reached, and that equilibrium will be when the net rate of heat transfer from the sensor is equal to 0. That is equal to the q dot convection to the sensor from the fluid is equal to the q dot radiation from the sensor to the wall, right? Now on a unit area basis, we can write this as q dot convection is equal to q dot radiation dividing by the area. Now q dot convection, we know the formula of q dot of heat transfer through convection is H A S Ts minus Tf. Now we are considering heat transfer through a unit area basis, so we'll have just H into the fluid temperature Tf and the wall temperature, sorry, the fluid temperature and the thermometer sensor temperature, and the q dot radiation from the sensor to the wall, assuming the thermometer sensor to be at a higher temperature. So from this we can get Tf to be Th plus epsilon sigma Th to the power 4 minus Tw to the power 4 by H. So this fluid temperature is the temperature of the thermometer plus an additional term. So to give a close approximation of the thermometer reading and the fluid temperature, we will have to make this as small as possible. So to make this equation as small as possible, we cannot change the value of sigma. The thermometer reading will obviously depend on the fluid and the application. So we have no control over this. We have no control over the wall temperature. We don't have control over H value, which is a constant as well. We have only the control of the value of epsilon. That is the emissivity of the sensor. So this emissivity, if it is as close, if it is as small as possible, will be better for us, and we can give a close approximation of the fluid temperature, and that would be almost equal to the thermometer reading. So if we try reducing epsilon to as small as possible, we can get a very good answer to our question. Now, for those applications, we will see epsilon to be low as possible. So for those applications, we will further see questions on how the epsilon value can be reduced. Like epsilon can be my zero point 0.1, zero point 0.2, and then you have values which are lesser than that also. But if epsilon is like 0.7, 0.6, you will have problems with the thermometer reading because you will have this factor as well, which will give you the answer.